So far, we've understood the turning effect of a force, or the moment. Now let's talk about how the turning effect of, or how an object, when it comes to moment, can be in equilibrium, meaning that it will not move. And it's pretty simple, so let's talk about conditions for its equilibrium. And it's not rocket science, and I think those of you who are comfortable with forces can come up with it very easily. And the idea is, if you have a seesaw and there's a force acting over here and another force acting over here, and there could be n number of forces and all over the place, the only thing you have to cater to is essentially that all the moments that are generating a clockwise moment, or all the forces that are generating a clockwise moment, should be equal to all the forces generating a counterclockwise moment. And once this is true, this entire system will be in equilibrium, because everything trying to turn it to clockwise is balanced by everything trying to turn it counterclockwise. So the forces don't have to be balanced. You could have one very small force over here, and that can be counteracted by one very large force, but a lot closer. So the effect of the smaller force, because it's further away, it's a lot larger. As long as the moments, both clockwise and counterclockwise, are equal, the system is in equilibrium. Or in other ways, a little more mathematical or a little more easier to verbalize definition would be to rearrange this equation. And I'll just bring the clockwise moment is on the same side. I'll bring the other moment over here and I'll subtract it. So this difference of the two moments, if it's equal to 0, or I can say the sum of these two moments, if it's equal to 0, this system, or any system, will be in equilibrium. And in words, you can write it like this, essentially meaning the equation which is right over here. The sum of all clockwise and counterclockwise moments, I forgot to add moments here, is equal to 0. And let's just write in moments. Forgot the most important word, moments. I forgot, so you guys don't forget. The sum of all counterclockwise and clockwise moments is equal to 0. That's the condition for equilibrium. Now let's take a look at how we can use this if a question shows up. The first force acting on this seesaw over here is 10 newtons. The second force acting on it halfway is 5 newtons. And you want to figure out what is the force F over here for this to stay in equilibrium, for the seesaw to stay in equilibrium. One very important part is the length of the seesaw is 1 meter, or this force is 1 meter away, which each of these forces are half a meter away, half a meters away, right? And the total would be from each other, and at least the 10 Newton force is 1 meter away, right? So what is the force that will keep this in equilibrium? So let's try calculating that. So you want it to be in equilibrium, so you want to say the sum of, you can say either way that they're equal, or the addition of both moments, counterclockwise will be equal to 0. I'll try it the other way around, is the all clockwise moments will be equal to all counterclockwise moments. So what's going to be clockwise? What forces over here are going to be clockwise? This is going to be counterclockwise. This is going to be again counterclockwise, and we have only this force being clockwise. So the first moment and the only moment that's going to be clockwise is by our force F, which we need to find out, which is at a distance of 1 meter away from the pivot. The second force, let's change our color. We'll talk about these two, but let's talk about this one first. This one is going to cause a counterclockwise moment, and it is also 1 meter away, plus it's assisted by a 5 Newton force that is half the distance away. So that's going to be 10 plus 2.5. F has to be 12.5 newtons. So if there's a force which is 12.5 newtons over here, this system will then be in equilibrium.